Okay, what does it look like if we have only single drainage, which means that the sand is only at the top? So this is a single drainage situation here. Why? Because I have rock at the bottom, I have sand or gravel at the top. Now, again, when we apply this fill, the gravel fill with the stress of sigma, what happens? I'm plotting my UXS. There's UXS 0. As soon as I apply the sigma, the UXS jumps to be a value of equal to sigma. That is at t equals 0 plus. So what I'm looking at is, again, this is the top of my clay layer. This is the bottom of the clay layer. But at the bottom, I have rock, and the pore pressure cannot dissipate at the bottom. It has to, it can only dissipate quickly at the top of the clay. So as a result, at the bottom of the clay, we have very slow pore pressure dissipation. And that's why we end up with these curves that look like this for each time period. The excess pore pressure remains high at the bottom of the clay. This is what takes place from t equals 0 plus to t equals infinity. We don't need a new solution curve. All we need to do is to take the solution curves that we have and ignore the bottom part. So in other words, we basically just cross off the bottom part. And so when we're using the solution curves, we have to recognize that this is the bottom of the clay. This is the top of the clay. And the middle of the clay is in here. So that's really all there is to it to handle the single drainage instead of the double drainage. The equations are the same. T is still C sub Vt over HDR squared. So the only change is that you're going to use only the top half of the solution curves. All right, I want to skip this for the time being. Come back to it later. Okay, I'm just going to show where these solution curves come from. And I'm not going to do the derivation. You've done this in your differential equations class. It comes from the heat transfer problem. You remember this. I think they do this in your class. If I have ice up above and ice up below, for instance, and I have something hot in the middle, well, what happens to the temperature with time? Well, like I say, it cools. It looks like this. It cools quickly at the bottom. It cools quickly at the top. And in the middle, it's the slowest to cool off. So, and what do we end up with? It's the same. These temperature curves with time are the same as the excess pore pressure curves. So it's the same equation. Everything's the same. And so in physics, in heat, you did that. So I'm not going to derive the differential equations. It's your basic heat transfer differential equation. For us, the form of the differential equation looks like this. Instead of temperature, we have excess pore pressure. And instead of some temperature property of the material or heat transfer property of the material, we have the coefficient of consolidation. So we use UXS U excess instead of temperature, C sub V coefficient of consolidation instead of a heat transfer coefficient. So this is what it looks like. Second derivative of U excess with respect to x is equal to C sub V times the second derivative of U excess with respect to time. So the answer, if we try to solve this differential equation, what we're solving for is U excess as a function of x and time, distance and time. Not distance, x coordinate and time. Okay, here is the solution to that equation. Again, we're not going to go through the whole solution. Supposedly you've done this already, so that's what you learned in your differential equations class. Is U excess is equal to 4 over pi times sigma V. Sigma V, that's the initial stress from the fill. The sum from n equals 0 to n equals infinity of the quantity 1 over 2n plus 1 times the sine of 2n plus 1 times pi x over 2h times e to the negative 2n plus 1 squared, pi squared times t, capital T, that's the capital T over 4. This semester, I'm not going to make you memorize this equation, so ignore that. Okay, so this equation gives us these curves. Again, we don't have to use the equation. We're just going to use the curves. Okay, so how do we do a problem? Okay, so let's look at this. At t equals 0 minus, I've got just clay. At t equals 0 plus to infinity, I have the sand fill and it sits there for infinity. Our point of interest will be at the center of the clay layer. That's where we're going to take it. Now notice the first thing that you need to understand is do I have single drainage or double drainage? And in this particular case, what do we see? Well, I have rock at the bottom. I have rock at the bottom, so I have single drainage. And then the only change that means for you, really, is that when you go into the excess pore pressure curves, you need to use only the top half of the chart. Okay, so here are our soil properties. The usual ones, we have the densities, C epsilon R, C epsilon C, C sub V, OCR. Our goal is to find the settlement at t equals 1, 5, and 20 years. Okay, as we said, the first thing you note is it's single drainage. And okay, I should say, okay, that's a good point. So there are two differences, really. You have to use the top half of the curves, but you also have to recognize that HDR equals H. HDR is equal to H, not H over 2. So two things that you got to keep in mind there. And what we're going to do, we're going to solve this problem. Our whole key to solving the problem is finding the U excess at the point of interest. Once we get that, it's a very simple problem to solve. Again, I want to emphasize that you need to memorize this equation. Capital T is equal to C sub VT over HDR squared. Okay, so the way that we're going to set up our spreadsheet is the following. We are interested in the times at 1, 5, and 20 years. So we're always going to be interested at the point of interest. We're going to look at the different times. So we're going to do the usual ones that we have, 0 minus, 0 plus, and infinity. And we're going to add to that the 1, 5, and 20 years because we were asked for it at 1, 5, and 20 years. So the first thing we do is convert the small t to the big T. So I'm going to simply note that, I guess I should put down that, note that our HDR in this case then, so since HDR equals H, then that means that HDR is equal to 8 feet, the total thickness of the clay layer. So HDR is 8 feet. We can now use this expression and this value of C sub V, this value of HDR, and we can convert the small t's into capital T's by simply plugging into that expression. So notice, of course, t is 0, t is infinity, capital T is infinity. At these and the intermediate times, by plugging into that expression, we get these values. We have to use what we knew before, which is that, what do I see? My sand fill is 5 feet thick. It's dry. The unit weight is 100. So 5 feet times 100 gives us 500 PSF, pounds per square foot. That means that at t equals 0 plus, UXS is 500. Now we have to use these values of t to get the UXS, to get the UXS factor. How do we do that? We go into the chart. Because this is single drainage, I've crossed off the bottom half of the chart. So that, in other words, this represents the bottom of the clay, this is the middle of the clay, this is the top of the clay. Our point of interest is at the middle of the clay. So we're going to get values at the middle of the clay. What I do is I look at my capital T. First capital T is 0.0469. Now, that's a tough one because our first, if I look here, this curve, this curve is for capital T of 0.1. Well, I don't go as low as 0.0469, so I'm going to create my own curve. Approximately, it looks like this. And I'm going to go in through here, the middle of the clay. I'm going to get this value here, and I'm going to read it off from the top, and I get 0.9. And I put that 0.9 here. My next capital T is 0.234. So I look at the curves. I have a capital T of 0.2 there, a capital T of 0.3 there. Well, I'm between those two. So I'm going to create this approximately, it's approximate, curve to represent 0.234. Again, I'm at the middle of the clay, so I come in here, I read this value, and I get 0.5. I put that 0.5 there. Then my last one, I get a capital T of 0.923. Again, it's between t equals 0.9, t equals 1 rather. I sketch in a curve approximately like that. I take the middle of the clay layer there, and then I read the value 0.08. I use the 0.08 there to get my excess pore pressure. So in other words, at 1 year, I have 0.9 times the UXS initial. At 5 years, I have 0.5 times UXS initial. 20 years, I have 0.08 UXS initial. Those all make sense because what do we realize? That as time goes on, the excess pore pressure dissipates. And so all of these numbers, as we go down, are decreasing, and that means that the pore pressures are dissipating. So we go back to our table, and here my UXS initial was 500. So I have 0.9 times 500, 0.5 times 500, and 0.08 times 500. And I get 450, 250, and 40 for. So that is my UXS. My U water table is easy to get. It doesn't change. It's simply the 4 feet times 62.4. Everywhere it stays the same as 250. And so okay, make sure that this is, so I get my pore pressure U is simply the sum of those two. I now have my, so continuing this spreadsheet, I have my U's at all the different times. So now I have to put on the sigmas. Again, to do the sigmas, I look at the correct picture. To get the sigma t equals 0 minus, I look at the t equals 0 minus picture. I get 520. To get the rest of the times, I look at the other picture. So you can all do that. And now it's just straightforward. Sigma v minus u gives me sigma v prime. So I get my sigma v primes. And at various times. So in other words, I'm learning what the sigma v prime is at 20 years, for instance. At 20 years, it's 730. And you can see that what happens to sigma v prime, well, it goes up and up and up. So as we go downhill, or down the spreadsheet, we see a greater and greater sigma v prime, which fits with what we know. Now what do we do? Now we have to use our OCR, our sigma prime p, etc. And for this particular case, the OCR was given to be, I believe it was 1, but let me double check here. Yeah, okay. The OCR is 1, which means what? If the OCR is 1, then we're always, looking down at the curve here, we're always going to be just in this range. So, in other words, sigma prime p is equal to sigma prime I, so I put the 270 there. That 270 came from there. And so we are simply going down in that way. So that means I'm only using the second part of the curve, the second slope, so I get 0.18 times log of that. You can all do this at this point. So what I'm doing is I'm now plugging in the sigma v prime, 320 there. The 520 goes there. The 730 goes there. The 770 goes there. I'm simply going down a little bit at a time down the curve. Notice that in each case, though, the denominator is always 270. It stays there for all of them. Or 270, 270, 270, 270. And that's my epsilon v. Delta H is H times epsilon v. And I get these numbers. I'm going to show you a different way to work this problem later. We're not going to pay attention to this, but we're going to do the same problem in a different way. Okay, I'm going to stop there.